Alrighty, well, this is the first video that I'm doing with my new document camera. I'm thinking that's going to work out better. I like it a whole lot better than the previous one. We'll see what the product looks like in the end. We're going to be doing section 5.5 in your book, which is integration by substitution. Now, here's the thing. You never ran into a problem that you couldn't differentiate, okay? There was never a problem that you couldn't differentiate. We had all these rules, and you had combination functions, and we had a way of differentiating product functions and sum functions and difference functions and quotient functions and composite functions and everything like that. I'm here to tell you that not everything can be integrated. Not all problems are in a form that are capable of integration. Now, some of them are very straightforward. The time for those, however, is over. Some of them are a little more indirect. And so really we have three classes of integrals: the easy ones, the impossible ones, and the ones where we need to employ techniques of integration. So this is technique, okay, number 1. That's what integration by substitution is. It's a technique where the integration is not exactly straightforward. Now remember back to when we were doing differentiation. When did it become difficult? Differentiation became difficult with the chain rule, right? The chain rule was the first time where you went, whoa, whoa, whoa. I mean, well, the quotient rule is a little bit difficult to memorize, but the concept wasn't all that hard. Chain rule was the first time where you regularly made mistakes because it had to deal with composite functions, okay? Integration by substitution, or what's called sometimes U sub, undoes the chain rule, okay? So if the first time you dealt with derivatives where it got really difficult was a chain rule, then obviously integration by substitution is going to be a little bit difficult, okay? Now here's the thing. We talked about how derivatives, okay, and integrals are inverses, right? They are inverse operations of each other. That means that they undo each other. Now, differentiation, there's a reason why we did differentiation first. Think about what it would take to undo a problem that is in a chain rule form, okay? So remember that when we take the derivative of f of g of x, we get f prime of g of x, g prime of x. Now, in order to go from here back to the composite function, it is not enough to have f prime of g of x dx. You have to have that second part right there. You have to have the g prime of x, okay? If the g prime of x is not there, you cannot undo it. Now, I'll give you a very simple example. If I have y is equal to sine of 2x, then y prime is equal to 2 cosine 2x, right? So if I have if I have cosine of 2x dx, I cannot integrate this in this form unless there is a 2 right here. Basically, this whole thing needs to be there in the integrand in order to successfully undo it, okay? Now, basically, U substitution, what I'm about to teach you, is just a way of ensuring that all the necessary parts are there in order to successfully undo the chain rule. So let's look at a relatively easy example. I have x squared minus 9 cubed times 2x dx. Okay? Now, this one is already completely filled out for me. Okay? This right here is my f prime of g of x. Okay? This right here is my g prime of x. 2x is the derivative of what's inside these parentheses. So this actually does wind up being what? Well, it winds up being 1/4 x squared minus 9 to the 4th plus c. And you're like, oh, there's just a whole lot going on there. It's hard to sort of see it all because there's just a lot going on. The benefit of u substitution is it gives me a way of cleaning up. It gives me a way of cleaning up the notation. Okay? So what I'm going to do is I'm going to let u be equal to x squared minus 9. Now if I take the derivative of that, that's going to be 2x, right? Now remember, we don't usually break this apart, or we haven't in the past, but that is a ratio, okay? And therefore du is equal to 2x dx. I have this, I have this. I have both of those in here, okay? So really my u stands in for my g of x, okay? And this winds up being, once I do the u substitution, u cubed du, right? Because here is my u, and here is my du. Now from here, it's a little bit more straightforward, right? Because it just looks like undoing the power rule, which of course it is. So you have 1/4 u to the 4th plus c, and then you just substitute back in the thing for which you substituted, and I wind up getting exactly the same thing I got up here. But here's the thing. Without a whole lot of practice, you're not going to, it's harder to see the integral straight here. It's easier to see it once you've done a little bit of substitution and significantly cleaned up the notation. Okay? So don't skip the u substitution during the first couple of days that you're doing this. Now some will become so easy after a while, like the one that we just did, where you'll go, okay, well cosine 2x dx, and you're like, okay, well already in my head I know that a 2 needs to go right there. Now can I just multiply the integrand by 2? Well, it's a constant. Sure, I can multiply it by 2, so long as I also multiply it by 1/2. Okay? And therefore, I'm going to get 1/2 integral cosine 2x 2 dx. Now, if I wanted to go, now from here it should be pretty easy to see that this is going to be 1/2 sine 2x plus c. But if I wanted to do my u sub, all I would have to do is say, well, u is my inside, right? The g of x, the inside of my composite function. Here, and usually when you're doing trig, it's going to be the angle measurement expression is going to be the inside. Usually, okay? Not always, but usually. And then, of course, du, if I take the derivative and multiply both sides by dx, I get 2 dx. Okay? So I have cosine of u. I needed the 2 in order to complete my du. Well, as long as you're multiplying by a constant, that's really not that big of a deal. So you multiply by 2, you multiply by 1/2. It transforms it into this, which in terms of my u substitution is just cosine u du. Well, that's relatively straightforward. That becomes sine u plus c. And of course, if you're going to substitute back in, you're going to get 1/2 sine 2x plus c. Okay? Now that's pretty much how it goes. You just have to figure out what is your inside, and sometimes that's easy and sometimes it's not. Then you have to figure out exactly how you need to change the integrand, if indeed you need to change it, in order for it to wind up being in a form that you can properly integrate. Okay, so the integrand, you need to be able to transform the integrand into a recognizable derivative of something such that you can undo that derivative. Okay? Well, let's do another example. And we have x cubed, x to the fourth plus 3 squared dx. Now, oftentimes when it's something like this, the first thing that you want to look for in terms of, candidates for your u value is, well, the parentheses, okay? And in this case, it actually is that straightforward. This is x to the fourth plus 3, okay? So that's u squared, okay? Let's see what du is. Okay, if I differentiate both sides and then multiply both sides by dx in order to sort of get in terms of a substitution form, I wind up with that. Well, do I have u? Well, yeah, I mean, u's right there. Do I have du? Well, I have two pieces of the du. I have the x cubed, right? And I have the dx. The only thing that I require now is I simply require a 4. So, if you want to go ahead and put it in this form so that you can see it, and then provide the 4, nullify it numerically by also multiplying by a 1/4. At this point you have, that's your u squared, that's your du. Okay, well, how do I integrate u squared? Well, u squared is really easy. Now, do you see how this is much more manageable in terms of notation than this? The u substitution is not absolutely necessary, but it gets rid of the distractions, okay? It gets rid of the distractions when you're trying to identify what is the inside, what is the g of x in the undoing of the chain rule. This winds up being, of course, 1/12 u cubed plus c, or 1/12 x to the fourth plus 3 cubed plus c. That right there is that integral. Okay? Well, let's go ahead and do one that's a little bit, well, let's not get too far ahead of ourselves, but let's go ahead and do x sine x squared dx. Now remember, when you're doing a trig one, the first thing that you need to look for in terms of a candidate for your u value, for your inside, is, of course, the angle measurement expression. And we'll just sort of play around with that. Is that indeed what you want to pick? Well, let's go ahead and see if when you differentiate that and find your differential, which is, of course, what this is called, you get 2x dx. Now, do I have all the elements of du? No, I have the x and I have the dx, but I'm missing the 2. But 2, like I said before, is a constant, and therefore it is you're perfectly capable of actually plugging it in, okay? And therefore what I need to do is I need to transform this into sine x squared x dx. I need to now provide my 2 right here, and of course nullify it numerically by multiplying by 1/2. And there, the multiplicative identity property, or multiplicative inverse property coming to the rescue. And this winds up being 1/2 sine u du, which winds up being negative 1/2 cosine u plus c, or negative 1/2 cosine x squared plus c. And you have simply used your u in order to get a distractingly complicated integrand into a very, very easy form, such that the integration is easy, and then all you have to do is substitute the u value back in. Okay, this has been sort of our first sort of excursion into u substitution. This is one of the most difficult sections in the entire book for most students. So I'm going to do quite a few videos on this to make sure that we have this under our belts. There are, of course, beyond mine, book oodles of tutorial videos on YouTube, so avail yourselves of those if you run out of mine. But be on the lookout for video number 2 here.